One. All right, so this is quiz 4 review. For this quiz, we have 2 problems that we're going to go over. Once again, it's just kind of like a rehash of the last week or two with Newton's second law, Newton's third law, just more complex problems, more moving parts of the problems. And then there's no like Hooke's law. There's no like spring force problems here on this quiz. They never tested us on it. I don't remember if the students were tested on it last semester. But there are a lot of really good examples in the slides that I'll post on the Google Drive. And then there's also like a select few problems on the online homework that I'll pinpoint as well. That'll be good to review. But generally, the spring force is just, once again, just another force that you add to the equation, right? So we have normal force, we have gravity, we have friction. And so spring force is just another one of those forces that you'll add. And so this week too, you guys are doing buoyant force. So it's just adding forces, and you're still kind of applying that basic concept, using Newton's second law and integrating all those forces, figuring out what's your net force in the x direction over the y direction and stuff like that. So maybe you get a new force with a new equation or something, but generally the same concept applies as to how to set up an equation for Newton's second law and stuff like that. So at the end of this quiz review, I will kind of go over some important things that you guys should review for this quiz. And then if you guys have any additional questions, or you want to ask questions about like the exam real quick afterwards, I'm more than happy to answer questions about that. Hopefully we can get done early, and then if you guys want to leave, that's fine as well. And then if you want to ask questions, that's also fine. So without further ado, I will go ahead and get started now with quiz 4 review. So problem 1 here is block on a slope, right? So it says consider the diagram on the right of a block of mass 6.5 kilograms, right? So I want to write, oops, that's a huge pen. Mass is 6.5 kilograms. And it's motionless on a frictionless inclined plane. So it's motionless and it's frictionless. So those are 2 important keywords there when figuring things out with this problem. So if it's motionless, we can kind of infer there using our intuition, well, if something's not in motion, there's no net force acting on it in any direction, right? So there's probably going to be a net force y component that's 0 and a net force x component that's 0. So F net x is equal to 0, F net y is equal to 0 because it's motionless, right? It's just suspended there on the inclined plane. And then at the same time, when doing and setting up those equations, right, we can tell that there's no friction, right? So we're not going to incorporate any sliding or kinetic friction, my bad. We're not going to incorporate any kinetic friction due to sliding between the box and the incline. So we don't have to factor in the friction force there either. But we also have this little tidbit here. Actually, let me turn on do not disturb so I don't get any notifications. Sorry about that. But we have it's kept fixed in place by the tension of a string attached to the wall. So this indicates that we have some kind of force of tension that's going to be a component in our F net equations, right? And then finally, we have this angle here. Theta is equal to 20 degrees. That's the angle of incline right there with respect to the horizontal, right? So you have the mass. We know that there's no friction. We know that there's no net force in any direction because it's motionless. And we have our angle, right? And so with that being said, we can kind of move on to part A now. It asks from us to draw a free body diagram using the coordinate system shown. I don't know, for some reason the coordinate system is always kind of marked out, but x is parallel to the slope and y is perpendicular to the slope. So this just means the tilted y and x coordinates that I've been talking about in previous sessions, and no doubt that your professors have mentioned as well, hopefully at least. And so it also says use the appropriate subscript for each vector and include the coordinates in your free body diagram. So this is what I'm talking about when it says include the coordinates. So they reminded you here. In future quizzes, they might not remind you to put your tilted coordinates, but trust me, it's worth points. Like, they will take points off if you don't have an indication of what your coordinates are. So first things first, right? Since they've indicated that x is parallel to the slope, and y is perpendicular, forming a right angle with the slope, that inclined plane, right? So that means we have tilted coordinates. So literally, in order to get, assuming that we have our free body diagram correct, in order to get those full 4 points, we also have to add this little asterisks here and say, okay, we have tilted coordinates. right? So tilted coordinates, so we can say like, I'm gonna draw a little triangle or something to kind of show that. And then say, okay, we have, oops, that is horrible. This is our tilted y. This is our tilted x. You can say that, and that's how you would kind of indicate what type of coordinate system you're using. And so now we can kind of move on to the free body diagram, right? So anyone want to give a shot as to which forces are acting on this box here, or this block? Yep, excellent. So we have tension force, and as shown in the picture here, that is along the incline of the slope. So that's based on our diagram here and based on the coordinates that we have labeled. That's along the tilted x-axis. So it's kind of up and to the right like that. So that's our force of tension, right? We have normal force, excellent. So we have normal force, that's the contact force, right? The force that is perpendicular to the surface of contact, that's giving solidity to the incline, right? It's preventing the box from just kind of sinking through it. And so that's perpendicular, like I said. And so we'd have normal force kind of pointing upwards like that, up and to the left, along that tilted y-axis. And then you have gravity, right? Force of gravity. That's always pointing straight down, like immediately straight down. Now, the mistake that a lot of students make, they'll say like, okay, well, force of gravity is along the negative y-axis, right? Well, that would be true if we didn't have tilted coordinates. So you have to remember that our y-axis here is kind of tilted, right? So if a force is like this, like that, right? Well, that's a little bit of, like if we had the force of gravity like this, right? That's a little bit of the y-axis, and it's a little bit of the x-axis too. So that's why often when we have these, or pretty much always that when we have these tilted kind of problems, right, where you have a box on an incline or something, you're always going to have these like FGY and FGX components. And I would pretty much advise to kind of draw them out anyway. As long as you have this type of problem, I'll just immediately put FGY and FGX as well. Because more likely than not, they're going to, there's going to be a part of the problem somewhere that's going to involve you trying to figure out those components or using those components to figure out another component. And so at the same time, when we have this angle of incline, they say that this is 20 degrees. Know that that 20 degrees is also the same measure of the angle here. So this is also 20 degrees. That's always the case. So whenever you have this angle of incline, if we're drawing our free body diagram like this where gravity is pointing downwards, and then we have this tilted y-axis where we have FGY and FGX, then know that this angle right here is the same as this little angle in that makeshift triangle that we're doing. So this little angle, like if we continued this triangle here, like this is the incline, this 20-degree angle is the same as this little 20-degree angle there in our little makeshift triangle. So that is the free body diagram for part A. Does that make sense for everyone? The only thing that I would actually add to this, and that's an adjustment, is considering the fact that this diagram or this problem says that the block is motionless, there's actually a mistake to this diagram. Can anyone tell me what the mistake is? I made a huge mistake actually that, like, depending on the TA, could lose me some points. But most likely lose me points in almost every scenario. It's very, very simple. I'll give you a hint. It has to do with like the length of the vectors. Yep, excellent. Force of tension is too big. It's way too huge, right? So if this force of tension has, let's say, if this was proportional to, let's say, like 60 newtons or something, and this FGX was 20 newtons, right? We can say like this maybe like about a third of the length. Then that would indicate that there's some net force in the x direction, that the force of tension is overwhelming that FGX. So there's a net force in the x direction, and that's not the case. So we'd actually have to kind of decrease the length a bit of the force of tension, right? So we'd actually have to make it kind of look like about this length maybe. To be proportionate. Does that make sense? So you always have to draw when you're drawing your free body diagrams, make sure that the length of your vectors all are kind of proportionate to the context of the problem. So if the block is motionless, right, then I want to make sure that all forces in the x direction, all forces in the y direction cancel each other out, right? So net normal force here is about the same length as the FGY force, and FGX is about the same length as FT. So these would cancel out. This is positive y, this is negative y, right? This is negative x, this is positive x. They're the same magnitude, different directions, they cancel out. So always make sure that your free body diagram is also proportional and make sense with the context of the problem. Sound good? FG, right? The length that you draw for FG, you're going to draw it straight down, and the way you're going to draw it will determine the lengths of FGX and FGY, right? So draw it to a certain length where, once again, that the FGY would cancel out with any forces in the y direction, or the normal force in that case, and then forces in the x direction as well. Well, that's too long, my bad, this way. So you draw your FG in a way where you make sure that the components cancel out with the other forces. And in the event that you do have, let's say, if you added friction or something else, right, then maybe somewhere, like you can kind of roughly draw it in terms of like making sure all your directions are right. Maybe you might get the proportions off, the length is a little bit off, based on like the information that you get from part B or part C, whatever in the problem, right, or in the information that you have from the initial description of the problem, that they said that like if it's clear now, like after your calculations and stuff, that FGX is like smaller than or greater than the force of friction, for example, if there was friction, then we'd have to draw friction smaller, for example. So it's kind of going back and forth where you're drawing the free body diagram to the best of your abilities initially, and then kind of going back and adjusting based on the values that you calculate or the information that's there given to you in the problem. So like you see, we drew the tension force correct in the same direction. It's just that we went back, checked the context of the problem. Oh, it's motionless, so it can't be that long. So you kind of do a double check, some sanity checks to make sure that your drawing is correct. But yeah, I think that should make sense, hopefully, for everyone. Let me know if you have any other questions about A, but I will move on to B for now. B asks us for the magnitude of the tension in the string, right? So we got to figure out the magnitude of the tension in the string. Well, we got to look at what force we have here. So that's tension, and that's in what direction, right? That's going to be in the x direction. So if we're looking at forces in the x direction, we're probably also going to want to figure out forces or how this force relates to the other forces in the x direction as well, right? So if we're talking about an x direction force, more likely than not, we're going to have to set up some kind of F net equation in the x direction to determine this force based on knowledge of other forces, right? So do we have direct knowledge of any of the other forces? We don't necessarily have like a Newton number, right? We don't know that a certain force is equal to a certain amount of newtons or something like that, but we do have a key piece of information that can help us figure out some other forces. What is that key piece of information? What force do you think we can determine based on the information given in the problem? Yeah, excellent. Force of gravity, right? Because we have that mass, 6.5 kilograms. So if we can figure out force of gravity, right, we have that. Well, that's not necessarily in the y direction, nor is it necessarily in the x direction, right? And so we do have this force of gravity. Well, what else do we have? What else can we make use of besides the force of gravity here? What other important piece of information do we have? The angle, right? 20 degrees. So using trig, right, sine, cosine, tangent, we can figure out FGX, for example, right? And if we have FGX, we want to figure out FT, and we know that F net X, based on the context of the problem, that it's motionless, so the problem is motionless, or the block is motionless, right? So that means your F net X is equal to 0, right? Your F net X is equal to 0 because it's motionless. So we can kind of now start to form a little equation here. So we know that F net x is 0. We know that F net x is made up of a tension force to the right and then a x component of the gravity to the left, right? That would mean that force of tension is equal to FGX, or at least the magnitude of FGX, right? Because the FGX force, let's say if this was, it could have a magnitude of 20 newtons, but it's technically negative 20 newtons, right? Because it's pointing to the negative tilted x-axis, right? Along that parallel line there, it's negative x-axis. So if we were to just ask what's the force of FGX, and if it was 20 newtons or something, it would have to be negative 20 newtons, right? The magnitude would then just be the absolute value of that, which is just 20 newtons, right? So if we're asking for the magnitude of FGX, we say 20 newtons, for example. If we're asking for what's the force, the FGX, right, then we just say negative 20 because we want to include that direction. But like I said, and if you've attended my previous sessions, you know that I like to include the negative signs in my equations built in, because then I have the magnitude already, right? So that way I can get magnitudes for my final answers. And so I can get the magnitude of tension right there. So with that being said, for FGX, once again, as I mentioned earlier, we can figure that out using trig, right? So we know that Fg is equal to mg, right? Someone stated earlier that we can use the mass to figure out the force of gravity. So that's 6.5 kilograms times 10 meters per second squared. That gives us 65 newtons, right, for our force of gravity. And then we know that this is 65 newtons, right? This is our hypotenuse. Basically, this is the longest side of the triangle. And then we can use trig, right? We have this 20 degree angle to figure out FGX. What trigonometric function can we use to figure out FGX? Do we use cosine, sine, or tangent? We use sine, right? Because sine is opposite over hypotenuse. Cosine would just be adjacent over hypotenuse. So we can use cosine to figure out FGY. But we use sine to figure out FGX because it's opposite to the angle over the hypotenuse. Does that make sense? Okay, cool. So for FGX, right, we know that FGX over FG is going to give us sine of 20 degrees. We know that FG is 65 newtons, so we'll multiply that over. So FGX should be equal to 65 sine 20, right? And then that should be equal to 22.2 newtons, I believe. So if FGX is 22.2 newtons, then FT is 22.2 newtons. Right? FT is 22.2 newtons. So, if I were to ask you, for example, individually, okay, what's the force of gravity here? I wouldn't be able to just say 65 newtons. I'd have to say negative 65. Well, actually, no, I take that back. Because we can't really define what the direction is per se, because it's kind of in the x direction and the y direction. But I guess in a general context, like if we didn't have tilted coordinates, right? If we were just negative y, positive y on a normal coordinate plane, right? If I were to ask you what the force of gravity is, it would be negative if the coordinates were normal and if they weren't tilted, right? I'm just kind of re-emphasizing that point just so that you know, like, the difference between magnitude and just asking what the force is. Because if you're asking for magnitude, then all your answers have to be positive, right? If you're asking for magnitude, answer must be positive. If you're asking for the force in general, then you have to be sure to include directions. So add a negative sign if the force is pointing in the negative y or in the negative x direction, for example. So the reason why I can't say this is negative 65 newtons, I almost made that mistake, is that because this is on the tilted coordinate system, right? And it's pointed this way. It's not necessarily on the y-axis, and it's not necessarily on the x-axis, right? So we could, in order to give a direction for this, right, we can't say like negative 65 newtons, but if we were to say something, this would come back to like the first 2 weeks. We'd say that, okay, if this was our coordinate plane, right, this tilted coordinate plane, then FG is 65 newtons, for example, like 20 degrees west of south, right? west of the south, right? So this is 20 degrees west of the south. If you remember that from the first 2 weeks where we did the directions and stuff, that'd kind of be the way to maybe go about describing it. But otherwise, yeah, hopefully that kind of made sense with regards to the whole magnitude and negative sign stuff. I just try to re-emphasize that because, like, no matter how many times I say it and now how many times it sounds redundant, like, there's millions of people that will, like, mess it up on the exam or on the quiz. They'll mess up the directions. It's a very, very common thing to do, and I'm one of them too, so it's not like I'm immune to this type of stuff. It's just very important to, like, be wary of it all the time. For FNet Y, that's what we're going to be doing in part C, actually, right? So if everyone's okay with part B, I can move on to part C now, because in part C they're asking, what is the magnitude of the normal force? Well, once again, normal force is unknown to us, right? But it's a y coordinate force, right? It's a force that's pointing in the tilted y-axis. So the other force that's pointing in the tilted y-axis is FGY, right? So we can set up an FNet Y equation because we want to figure out this value of this force in the tilted y direction relative to the other values that we know or we can figure out that are also in the y direction. So what is the only other force that's in the tilted y direction that we know or that we can figure out? That's FGY, right? So if we can figure out FGY, the only way to relate FGY to Fn is by setting up an FNet Y equation, by considering what forces are acting in that y direction to figure out the net force. We know that the net force in the y direction, since the problem said the block was motionless, should be 0, right? Because it's not moving up or down, left or right. It should be 0 newtons. And then we know that Fn is pointed in the positive tilted y-axis direction, and Fgy is pointed in the negative tilted y-axis direction. That would indicate, once again, that Fn is equal to Fgy, right? Now, similar to this step here, how can we figure out Fgy? Yep, cosine, right? So cosine of 20 should be equal to Fgy, that's adjacent over hypotenuse, which is Fg. And so we know Fg to be 65 newtons, so 65 times cosine 20 should give us Fgy, and then that should be equal to 61.1 newtons, I believe. So your normal force should be 61.1 newtons, right? That's the magnitude of your normal force. That makes sense, right? So yeah, I mean, a common question is that, like, how do I figure out when or if I need to set up an FNet equation, right? You set up, the reason for an FNet equation is to figure out an unknown force or an unknown quantity or value of a force, right? Relative to other quantities of forces that you might know already based on what the problem is giving to you, or based on, like, forces that you might be able to figure out given the information in the problem. So we weren't given any forces explicitly, right? But we do know that there is a mass of 6.5 kilograms attributed to this block here. Well, mass is 6.5 kilograms, right? How does that relate to the rest of the frickin' problem, right? Well, I gotta think, okay, mass, and I'm looking for a force, right? Force, mass, force. Okay, well, I only have mass, right? That's the only value I have. How am I supposed to get forces, right? Well, I think about, okay, well, what force might be able to give me some idea or some relation to the mass? Okay, well, that's the force of gravity, right? Force of gravity is equal to mg. Well, there's the mass, and I know the acceleration due to gravity is 10 meters per second squared. So, okay, fine. I get the force of gravity now, right? Well, how does that help me figure things out? Well, now, for part B, for example, we were looking for a force in the x direction. Okay, cool, x direction. Well, Fg isn't necessarily in the x direction because of this tilted coordinate system, right? Well, how am I supposed to figure everything else out? Well, based on your free body diagram, you have that angle, you have components Fgx, Fgy. Okay, I can use Fg to figure out the Fgx component, for example, using trig. If I have Fgx, Well, that's a known force in the x direction. Okay, awesome. I have a force in the x direction now. I'm still trying to figure out the other force, tension. Well, how can I figure that out? Well, we know that there's no motion at all. There's no net force, therefore, in the x direction. Well, if I know there's no net force, right, and I know the value of FGX, and I want to figure out tension, what do? Well, that's where you set up a net force equation to kind of state what the net force is. It's 0 in this case, right? That's the context in the problem. And then you relate all the other forces together, right? What are the forces acting in the x direction? Ft and FGX. Give them the right signs. Solve for Ft, right? Based on the information that you can calculate, right? Because we calculated Fg using the mass. We used trig to figure out Fgx. We set Ft equal to Fgx based on the context of the problem. We got Ft. Same thing for the y direction. So setting up, figuring out whether or not you need to set up an FNet equation, like that's a very common question. And the idea is it always comes back to what's given and what's unknown. Like that's the whole idea of physics when you're solving any of these problems. What's given, what's unknown. Oh, I have mass. I know that the block is motionless. So I have to interpret all these things, look at what's given to me, what do I need to figure out? So it's the key to figuring out these types of problems is just and figuring out whether or not you need to set up a FNet equation is to look at what you need to figure out. If you need to figure out a force, right, then you're most likely going to have to relate it to other forces that or that you can figure out, for example. In some cases too, like if, for example, you just have a flat surface, like no tilted coordinate whatsoever. If I have this flat surface and a box is right here, I have some normal force, some Fg pointing downwards, right? Well, if I have the mass of the block and I'm trying to figure out the force, the normal force, right? Well, I can do Fg is equal to mg. I have the mass. I can multiply the acceleration due to gravity. I have the Fg. Okay, well, if the block is motionless based on the context of the problem, the information that they're giving to me, or they might not even state it. They might just say that the block is just resting on the surface, right? So you can infer that, okay, if it's resting, it's probably not moving, right? So in that case, like the forces should cancel out logically. So in that case, you might not even need to set up a net force equation necessarily because you're like, okay, well, if this box weighs 60 kilograms, so its force is 600 newtons in the negative y direction. So there's probably going to have to be a normal force of positive 600 newtons to prevent that box from sinking through the floor, canceling out all the net y forces, right? Keeping everything in a balance. So sorry for kind of like the rant there about like figuring out how to calculate forces and stuff, but I figured I got a couple questions about it. So I just wanted to kind of address when to use an FNet equation and why we need to use it and how to use it. So hopefully that makes sense for problem 1 and in general for how to figure out when you need to use an FNet equation. Sound good? Okay, cool. Alrighty. So if there aren't any other questions about problem 1, I'll move on to problem 2 now. So problem 2 is a happy hippo pushing a box against a wall. So it says a happy hippo has a heavy box which he wants to keep off the ground. He is, however, cursed with a hippo brain and therefore not smart enough to hold it from beneath. Such as it is, our hippo protagonist is keeping the box from falling by pressing it horizontally against the wall, holding it in place. The coefficient of friction of the box with the wall is 0.9 and the box has a mass of 350 kilograms. You may ignore friction between the hippo's hand and the box. So this is very, poor hippo. This is like Walmart version of Winnie the Pooh, but hippo style, I guess. So there you go. I think they had one of our quizzes. I remember they had us. I'll show you guys will see it, but I can't remember. They had like when we were doing like centripetal motion, they had an Among Us like character because it was popular at the time, on like a motorbike, and he was like traveling, like going like in a loop-de-loop, and we were trying to figure out forces and stuff, and it was just, I was not in the mood to see an Among Us character in the middle of my physics quiz. Like, I'm trying to figure out forces. I'm not in the mood to figure that stuff out. But hey, I guess it's a nice change, I suppose. But anyway, we have our mass is 350 kilograms for that. Whoa. Okay, the box is 300. For some reason I was thinking the hippo is 350 kilograms. I was like, okay, that makes sense. Box is 350 kilograms. That's insane. But yeah, mass is 350 kilograms. Our mu, our coefficient of friction, is 0.9, right? Now it says ignore the friction between the hippo's hand and the box, which is like right here between these two surfaces. We don't have to factor that in, so that's irrelevant. But we do have to factor in the friction between the box and the wall. So another thing is that the box is being kept off the ground, right? It's being kept from falling. So therefore, do we have a net force in any direction? Think about the context of the problem again. Yep, excellent. So I can see where some of you might say like, oh yeah, to the left because of the normal force, for example. The one thing that you might not be considering is the fact that, well, how is this box being like pushed up against the wall? There's an F push force, right? This hippo isn't like a magical hippopotamus, right? So, oh yeah, no, that's fine. Yeah, so maybe I said normal force and I didn't notice, but yeah, I was talking about net force. Like there should be zero net force because both in the y direction and in the x direction, all forces cancel out. And so when we're drawing our free body diagram, it says show all the forces acting on the box, include your choice of coordinates. Once again, you have to include your choice of coordinates. So if it's tilted, say tilted. If it's on incline. If it's normal, you just say normal coordinates. And label all force vectors with appropriate subscripts. So we have this free body diagram here. What force, anyone want to give some suggestions as to which forces are acting in the y or x direction or whatever? Yep, we have Fg. Force of gravity, so we have normal force. And normal force is going to be pointing in which direction? It's just kind of a review of the last couple of weeks. Would normal force be pointing up? Excellent, right? So normal force is always defined as the force that is perpendicular to the contact surface. So our wall is our contact surface. Perpendicular means forming a right angle with. So if we have the force like that, that's parallel, right? But if we have the force like this, oh, it forms a right angle there, right? Just also think of the normal force once again as the force that's giving solidity to the wall. So the wall here is solid, right? If I were to push with this box against the wall, if that wall was like, let's say made out of cardboard or something, and if I pushed against it, oh, it's just going to fall over. There's no solidity, right? But there's a normal force exerted back on the box perpendicular to the contact surface, forming a right angle with the contact surface to give the wall some solidity, right? It prevents the box from just floating through, moving through the wall, right? That's the idea of the normal force there. So yeah, normal force should be pointing to the left. Does that make sense? I can't see who asked the question. I'm just writing stuff down at the moment. But yeah, does that make sense? Because then we also have an F push. Do you need like more clarification as to why that normal force is pointing in the left direction? Because I mean, like, think about if I push this box to the right. If I pushed it to the right, if there's no force acting back on that box is going to go straight through the wall. It's going to keep moving, right? Because I'm applying some kind of net force at that point. That push is being applied to where I'll be moving in the right positive x direction. Now, because the box isn't moving at all, right, based on the context of the problem, there has to be a normal force, which is the force that gives some kind of solidness to the surface, right? So the normal force here, right, if I'm pushing with F push to the right, let's say 350 newtons, for example, that wall also has to exert a normal force, Fn, that opposes that force, right? Because without this normal force, without some force being exerted by the surface back on that push force, back on that object, basically, that object is going to go straight through the wall. So if I go back to that kind of cardboard example, right? If I were to, like, if I had like a cardboard sign or something, right, and I put my hand up against it and I leaned, right, if I wanted to lean, lean on that poster, for example, I would just topple over, right? Because there's no solidity to that cardboard sign, for example, right? But if that wall is solid, right, it's made out of drywall, and I literally, like, we're all in probably our own rooms, or maybe we're on campus or something. If I lean on the wall, right, I can definitely lean on the wall because there's solidity to that wall. That wall is applying a normal force acting against me leaning on it, right? So if I have a leaning force, for example, if I'm leaning on that wall is going to exert a normal force perpendicular to that contact. So if I'm contacting it here, for example, along this wall, along this y-axis basically, then I have the normal force would be exerted along the x-axis. Why? Because I'm pushing along the x-axis. So think of it as, okay, what's my surface and what's perpendicular to it? So if I have like that example earlier where I had the box, right? Well, the box is being pulled down by gravity, right? In order to prevent the box from sinking through the floor, that surface of contact, that floor, that carpet floor, for example, or hardwood floor or whatever, would have to exert a force back upwards, right? So if that box or that hand that I'm leaning on with is exerting a force in the negative y direction due to gravity, or if I'm pushing in the x direction, then I'd have to have that force, the normal force, be exerting in the opposite direction. And more specifically, it would be perpendicular to the contact surface. So if my contact surface is a floor along the x-axis, then the normal force is being pointed up perpendicular, forming a right angle with the surface, and it also should be opposing the other forces in the y direction if it's along the horizontal axis. Now, if it's this wall, for example, if I'm pushing this way and my contact surface is the y-axis, basically like a wall, right, going up and down, so the normal force would be pointed perpendicular to, forming a right angle with, right, the contact surface. And it also has to point in the direction to oppose the forces that are acting on the wall. So if I'm pushing in the right direction on a up and down wall along the y-axis, the contact surface is up and down. So the force, the normal force, would have to be forming in the left or right direction. Well, how do you determine if it's pointing in the left or right direction? It points in the direction to oppose the forces acting on it. So if I have a force that's acting on it to the right, best believe that normal force is going to be acting to the left to prevent that object from sinking through the floor, to prevent that object from toppling over and going through the wall, for example, in that cardboard example, right? So that's the idea of a normal force. It's giving solidity to the object, opposing any forces acting against it. And the normal force is always perpendicular to the contact surface. Does that sound good? Go ahead. Yeah, this is an old quiz. Yep, no worries. And I'll have it uploaded on Google Drive if you missed the first part, so you can see kind of what's going on here. Obviously, the videos will be uploaded as well. But yeah. Yep, that's a free body diagram of the box. There is, yes. I just haven't gotten to it quite yet. No worries, because it says the coefficient of friction of the box with the wall is 0.9. So, and they said to ignore the friction between the hand and the box. So we're only factoring in the friction in between the box and the wall. So, in that case, we would have friction pointing in what direction now? This is F push. Yep. Because once again, this box is being held stationary, right? And so if we're pushing to the right, we have a normal force to the left to oppose it. That cancels out the forces in the x-axis. We have gravity pulling it downwards. So we should have a static friction force pointing upwards to prevent it from slipping, basically, and moving downwards. The only time that you would use kinetic friction is if the box is already in motion. Since it's not in motion, we're referring to the friction force here as static friction. So let's think of static, like just not moving, right? And so the reason why it's also in the positive y direction, it's moving upwards, right, is think about if, like, okay, if I just let it go, right, then force of gravity would kind of be in free fall, so it'd be pulling it downwards. And so we have to have that static friction force opposing the gravity to keep it not moving in the y-axis direction. When I say forces cancel out, I mean that if you were to add up the forces in the y direction, they would be like, they would just essentially add up to a net force of 0. So if I had a static friction force of 300 newtons, right, and a gravity force of negative 300 newtons, well, if I added them up, 300 minus 300, that's 0. So I have to make sure that my forces are going to be opposite each other, equal in magnitude, essentially. They won't always necessarily be equal in magnitude, because, for example, like if you have static friction force and you had maybe another force acting also in the y direction, you had this force of gravity, well, this might be like, this force of static friction might be 150, the other force might be 150, and then gravity might be 300. But 150 plus 150, that's positive 300 newtons in the y direction, and then a negative 300 newtons in the negative y direction, right? So I have to make sure that everything acting in the y direction and everything acting in the x direction add up to a net force of 0. That's if the object is not in motion at all. Same thing for that first problem, right? I want to make sure that all the forces acting in the x direction, positive x, negative x, they add up to 0, and all the forces in the positive y, negative y direction, when I add them up, they equal 0. And that's what we did here. F net x is equal to 0. Tension force minus the FGX force, that equals 0. Normal force minus the FGY force, so normal force minus FGY is equal to 0. Tension force minus FGX is equal to 0. So when I say cancel out, I mean that when you add them up, the net force should be 0, given the fact that this box isn't moving. This one, yeah, because the object isn't moving, so the forces in the x-axis should all add up to be 0. Yep, no problem. So I think with that being said, for part A, that's our free body diagram. We have our static friction force, force of gravity, F push, and the normal force. Does that make sense for part A so far? Okay, cool. So part B now, it says, what is the minimum pushing force the Happy Hippo must exert to keep the box from sliding down the wall? So there's a bit of a runaround when you're trying to figure this out. It's a massive 6-point problem, right? And there's a lot of moving parts. So first of all, we got to figure out what's unknown. We want to figure out what the F push force is, right? We don't know what the F push force is. Well, we also have the mass, right? It's 350 kilograms. Well, if we're trying to figure out a force, there we go. If we're trying to figure out a force of push, right? Some force, remember what I said earlier about when you use F net equations and stuff? Well, if I'm trying to figure out a push force and I have access to a mass, right? Well, okay, what forces relate to mass? Okay, force of gravity, right? So I can immediately figure out force of gravity. That's mg, so that's 350 kilograms times 10 meters per second squared, right? And so there I should get 3,500 newtons for my force of gravity. Or technically negative 3,500 newtons, right? Because it's pointing in the negative y direction. But I'll keep it the magnitude for now. So I'll just indicate that this is absolute value, so this is just magnitude for now. And so we have our FG now, right? We want to figure out F push. Now, the thing is, if we want to figure out F push, we also know that it relates to the normal force, right? F push should be equal in magnitude, opposite direction, the normal force, right? Now, here's where it gets kind of complicated. How does this all kind of relate to each other? That's the big question here. Well, I have mass here, I have this force of gravity that's acting in the y direction. I'm trying to figure out F push that's in the x direction. Well, those are two different directions. It doesn't make any sense. And I don't know what normal force is, so I can't figure out F push. And I don't know what static friction force is, right? Well, then you kind of have to do some cross, like, directional action here, right? Because you kind of have to think about, okay, well, I have this force here that's in the y direction. I'm trying to figure out this x force. Well, here are some other unknowns, right? So how can some of the x forces relate to the y forces? Do any of you guys see a relationship between Fg and Fs, Fg and Fn, Fn and Fs? Anyone see a relationship? There we go. So, static friction force, the maximum static friction force, that is, the maximum static friction force is mu times the normal force, right? This is Fs max. You cannot use this equation whenever you like. You can only use it when the static friction force is at its maximum. Now, let's go back and think about the problem again, right? So, it says, what is the minimum pushing force, right? Well, if I'm pushing at a minimum, my bad. If I'm pushing at a minimum, right, then let's kind of imagine that box, right? If I have the box in between my hand and the wall, if I push on it really hard, it's going to continue to remain stationary, right? So if I start to relieve a little bit of that pressure, let's try and think about this like outside of the physics context and more like real life. If I were to relieve some of that pressure from the box, what do you think will start happening to the box? Is it going to stay? Or what's going to happen? It'll slip, right? So what is the static friction force here? How do we define that, right? What is that friction force of? Because we know that kinetic friction, for example, is the friction force that acts when two objects are sliding against one another or between one another, right? So the static friction force then is what? How do we define that friction force? Exactly. So it's the friction force that prevents slippage, right? So if I'm giving the minimum possible pushing force, what does that mean for my static friction force? Because if I'm maximum, yeah, absolutely right. Because if I'm giving as little pressure as possible, then, right, if I were to say, okay, if I'm applying, let's say 100 newtons, as soon as I apply 99.9, it's over with. That box is sliding, right? And so at that point, the static friction force is working at its absolute maximum to just barely prevent any slippage. So I have to think about this as if the minimum pushing force means that my static friction force is at its maximum. It's putting in the most work possible to prevent the object from slipping. Static friction force refers to the friction force that prevents an object from slipping, right? My hand is preventing the object from slipping, right? Because I'm pushing up against that box on the wall, right? If I start to relieve that pressure up to a certain minimum, then that's where the static friction force has to come in and be like, okay, we got to up the level, right? We have to increase the static friction force up to its maximum, right? To just barely prevent the object from slipping. Does that make sense? Okay. Makes sense for everyone else as well? So in terms of the problem, right, we know that the static friction force, when it's at its maximum, it's mu times Fn, right? We know that mu, the coefficient of friction, is 0.9. Well, what's Fn? How can we get Fn? Well, we're not quite sure yet, but we can get Fs. How can we get static friction force? Yeah, essentially we're using the maximum, right? We're using the maximum static friction force to find the normal force. But why do we need to find the normal force? That's the main question, right? Why is the normal force important? To find F push, right? Because we know that the F net X and F net Y are equal to 0. So if I have F net is equal to 0, and I know that normal force is equal to some value that I'm about to calculate, right? Once I find normal force, well, F push will just be the same value, just in a different direction. It'll be the same magnitude, opposite direction, right? It's kind of similar to that first problem, right? Where I didn't know tension, but I could figure out FGX. Once I figure out FGX and I know that my F net X is 0, well, I can set it up an equation and I can figure out what FT is from FGX. So that's what I'm trying to do here. But it's just a lot of, jumping across to figure things out, because first of all, the problem only gives me mass and I can figure out force of gravity, right? Well, from force of gravity, based on an F net Y equation, I know that F net Y is equal to 0 because there's no motion along the Y axis. So I can figure out static friction force from that, right? I can very quickly figure that out. And so if I do F net Y, that's equal to 0, and that's equal to Fs prime minus Fg, and that's Fs max, by the way, because there's a minimum pushing force. And so Fs prime is equal to Fg then. And we know that Fg is equal to 3,500 newtons, so Fs prime should be equal to 3,500 newtons, right? And so, yeah, go ahead. So if Fs was bigger than the force of gravity, we would have that's kind of a weird question, just because, in that case, you would have a net force in the Y direction, right? And so that would mean, I guess it's kind of weird. Yes, in that case, the object would be moving, and so in that case, it wouldn't be static friction anymore. It would have to be kinetic friction. So that'd be kind of weird, just because I don't think that's quite possible in this case, where you would have your static friction force, or even kinetic friction, be greater than gravity. Because if it is greater than gravity, right? Yeah, someone said you'd just be floating, essentially. Yeah, if gravity is bigger, right? If gravity is bigger, then at that point, there'd be a net force downwards, and so there'd be acceleration downwards, right? And so the box would be sliding down that wall, and once you're sliding, you have kinetic friction. Yeah, absolutely. But yeah, in this case, Fs technically would have to be smaller at every single, or almost every single, interval, just because this would be our maximum static friction force. So there's minimal static friction forces, right? Because it's I don't know, it's kind of weird to describe it, but basically, if you're pushing against that wall, right, and you're keeping things constant in the x direction, gravity would cancel out the static friction force, but the static friction force, it isn't at its maximum until you apply a minimum pushing force. Because it's almost like, the informal way to describe it is that, really, when you're pushing against that box with a really high force, right, it's almost as if the only forces that are really kicking in are the x-axis forces, right? Because you're really pushing against that box to not move in the x-axis. And then for gravity, right, the static friction force, it technically should be equal to gravity, but it's kind of weird, because I don't know, it's really tough to explain it. Okay, I'm trying to think of a better way to explain this, because your static friction force isn't at a maximum until you apply a minimum pushing force. But let's say you apply, I don't know, anything greater than that minimum pushing force. So if we said the minimum pushing force was like 200 newtons, if I applied 300 newtons, right, I'd still experience no motion for that box. But in that case, like, I can't really say necessarily that my static friction force is at a maximum because I'm not applying the minimum pushing force. So I wouldn't even like worry about that. I would just still think about gravity canceling out static friction force there. Yeah, it's kind of weird how I don't want to say like there's no static friction force in that sense, because you in that case, like, if static friction force is smaller than that maximum, then it would make sense that gravity would be pulling it downwards, which isn't the case, because if like you hold a box up against a wall, right, it's not going to move if you're applying like a decent amount of force. It's just the concept of static friction force here when it's at its maximum. That's when you have a minimum pushing force. Static friction force is always there. It's just that it's one of those forces where like it's variable in a sense, because it'll increase up to that maximum based on the forces that you're applying here. So if I'm applying a minimum pushing force, let's say the minimum is 200 newtons, right? I'm applying 500, right? So in a sense, the static friction force, let's say maybe that's, I don't know, like 300 newtons or whatever, right? If I drop down my 500 newton force of pushing to 250, right, that static friction force is going to go up because, oh, well, there's less push force now, right? That box is starting to slip, and so the static friction force needs to like up its work level to prevent that slippage. So static friction force is kind of a weird force because it's variable and it has to increase based on the amount of force that you're putting in, basically. And so I don't want to really say that outside of the maximum that they won't cancel out, because it just doesn't make sense if they don't. I'm not really sure where that gray area is, but okay, I'll stop the rant and let's just think about the, there we go. The maximum static friction force for the moment. No worries at all. Because yeah, it's just you kind of get into this gray area where it's a little weird, and I'm like not quite sure how to think about it in that sense. But now that we have our static friction force, right, this 3,500 newtons, we can set it equal. Fs max is equal to mu times Fn. So this is 3,500 newtons is equal to 0.9 times Fn. So Fn should be equal to around, what is it? Like 3,900 newtons, I think. Someone want to check that? Let me grab my calculator here and check it as well. At 3,888. Yeah. 3,888 newtons, right? That's our normal force. And so now we can start thinking about the x-axis forces, right? So F net x is equal to 0 because the box is not in motion. And we have F push to the right and normal force to the left, right? So F push in that case would just be equal to the normal force, and that's just equal to 3,888 newtons. So does that kind of run around there with jumping from y forces to x forces and figuring things out using the static friction force kind of makes sense there? All right. And so, yeah, I mean, Yeah, I'm not quite sure. I'm just trying to still think about the static friction thing because, I mean, gravity's constant, right? That mass is still 350 kilograms always. It's just now that um, the static friction force is kind of defined as a variable force. It can increase, it can ramp up um, if you're pushing with the minimal force, right? Because if I push that box really hard up against the wall, um, static friction force won't be huge, right? Because I'm pushing so hard that it doesn't have to do as much work per se. And then if I let go a little bit, relieve some of that pressure, it's going to start slipping. And so in order to prevent that slippage, static friction force is going to increase a lot to counteract gravity and keep the box from sliding down. But yeah, I mean, that idea of maximum static friction force and minimum pushing force, hopefully that kind of makes sense. Does that sound good so far? I would honestly just worry about this type of context. Like I wouldn't even worry about an idea where like I would still draw your free body diagram Fs, Fg, and I would just keep in mind that your static friction force is at its maximum, right? It's at its maximum when the object is just about to slip. So that's often a keyword that you're gonna like. You're for sure gonna see that in a problem, either in a quiz or exam or whatever. Well, they're gonna say like, okay, if we're gonna do this, I think next week or something with like centripetal motion. So like if you're on a roller coaster ride or something on a loop-de-loop, right? They'll ask you like, okay, what's the minimum force that is gonna keep the roller coaster in contact with the track or for something like that. So when you're at a minimum for, or let's say for example, like if you're parked on an incline, right? So there's gonna be a minimum static friction force or a maximum static friction force. My bad, a maximum static friction force that is gonna prevent the car from slipping on that incline. So if also like if you're turning on an intersection, right? If you're making that turn, there's a maximum static friction force, for example, that'll just keep the tires from slipping. So that's the idea of maximum static friction force. It's never at its maximum until the object is just about to slip. So if you ever see like in a problem like, oh, the object is about to slip or something, then know your static friction force is at a maximum. Otherwise, like the direction of static friction force and stuff, that should just be based on your free body diagram, based on the context of the problem. And in this case, you're pushing with a force to the right on that box, and then there's a normal force to the left counteracting that x-axis force. And so in that case, you have a gravity force downwards in the negative y direction, and then you have to have a static friction force between the box and the wall that is going to keep that wall kind of stationary there. But yeah, it's just kind of weird. There's this little gray area with the fact that static friction force is variable. And so hopefully, I guess, at least the free body diagrams kind of make sense in that sense. And the whole idea of maximum static friction force only applies if the object is about to slip also makes sense. But yeah, that's it for the actual like problems for the quiz review. And then I will move on to pinpointing some important problems on the different homeworks and on the slides and stuff. And then we'll probably call it a night. Sound good? All right. Any other questions about problem 1, problem 2? Anyone confused at all? I hope not. I know that last bit there was a little confusing, even to me, honestly. So please let me know if you're still kind of iffy. I mean, static, like a minimum would just be 0, that there's no static friction force. Because I think there's like a part of that equation too is the fact that like static friction force is less than or equal to mu times Fn. And so, I mean, you can have a static friction force of 0, but in that case, like, I guess the object would technically be in motion at that point because you would have kinetic friction. You would no longer have static friction. Scroll back down. Yeah. Yep. Everyone ready to kind of move on to the problems and stuff in the slides? Okay, cool. So give me 1 second here. Alrighty, so for the slides, I'm going to scroll up here and kind of take it one by one. So since they don't have anything included about springs, I would for sure go over, and I'll, like I said, if you're not in Dr. DeJong's section and these slides look unfamiliar to you, I will upload them as well so you guys have access to that. But I would definitely review springs on your professor's slides because there's not a lot of examples in any of the homeworks, honestly. In the quiz review that I just did, they didn't have a spring problem on there. So I'd highly recommend reviewing Hooke's law. So spring force is equal to the spring constant times the displacement, right? Displacement of the string. And think about spring force as being a restoring force. And so a restoring force just means that, okay, well, if I, for example, push the spring to the right, in order to restore the original position of the spring force has to point in the opposite direction of the displacement that you made. If I pulled it, for example, to the left, the spring force is going to try to restore that original position to the right. So that's the idea of spring force there. And then if they ask you, like, which spring has the largest spring constant, for example, spring constant would just be, based on the equation, would be spring force divided by the displacement. And so that's kind of like your slope, basically. And so if you have a steeper slope on a force versus displacement graph, then that steeper slope would indicate a larger spring constant. Yeah, the spring force equation has it's F equals negative kx if we're not looking at magnitude. F equals negative kx. And that makes sense, right? Because I was just talking about the fact that it's a restoring force. So say, for example, if I pushed it to the right, F equals negative kx, let's say that K was this is negative 100, right? If I pushed it 3 centimeters, then it'd be negative 300 newtons is the spring force. Why? Because it's trying, if I'm pushing to the right, it's trying to restore the original position to the left. Does that make sense? Yeah, so the formula, the absolute value for the spring force is K times the absolute value of the displacement, or delta x, delta L is the same thing. But if you're trying to just figure out what the force is without the magnitude, it's spring force is equal to negative the spring constant times your displacement. So if I have a positive displacement, I'm pushing it to the right, that spring force is going to be in the opposite direction. It'll be a negative 300 newtons, for example, or negative 100 newtons to restore the original position to the left. So if you like push on a spring, for example, right, it's going to want to return back to its original position. Or if you pull it, it's going to return back to its original position. So if I push to the right, it's going to want to extend back to the left. If I pull to the left, it's going to want to shrink back to the right. So your spring force is opposite the direction of your displacement, basically. Yeah. Is a larger spring constant be more stiff? Yeah, larger K measures spring stiffness, so bigger K means a stiffer spring. Like I said, steeper slope on an FSP versus delta L or delta X graph, a stiffer steeper slope would mean a larger K and therefore a stiffer spring. These are just really basic, like very quick calculation type problems where you just plug in a force, figure out the displacement and stuff. Like I said at the beginning of the quiz review, spring force is just another force that you add to the equation where you're trying to figure out the net forces and stuff. And so, you know how we did like normal force and mg for a couple weeks, and even this week, right? Now, for example, if you have a spring that's suspending this block, right? Well, it's not going to be normal force anymore because you don't have a contact surface. The block isn't in contact with a wall or a floor, but you do have a spring force that's going to be pulling it upwards, and this gravity pulling it downwards. And like I said, the reason why the spring force would be pointing upwards here is if that block is pulling it down, if the delta x is negative, or the delta y in this case, right, it's pulling it downwards, the spring force is going to want to point in the opposite direction to restore the original form of the spring. So the spring was like really coiled like this, and I pulled it down this way where the box is. If I let go, if I remove that box, it's going to want to move back upwards and shrink back to its original position, to its compressed position. So spring force is always pointed opposite the direction of your displacement. But yeah, I mean, really the spring force stuff, there's not much on it, unfortunately, not many examples, but it's kind of the same idea where you're just, once again, adding another force to the equation, to the concept of Newton's second law, Newton's third law, when you're trying to figure out the net forces and stuff. So I kind of maybe just make sure that you understand what all the different components of the spring force are, the K, the X, why there's a negative sign, stuff like that, and make sure you do like 1 or 2 example problems just so you're understanding like their units too, because spring constant is in newtons per meter. Make sure you understand the units as well and get kind of familiar with the math for it. Apparent weight, I don't think there's a lot of apparent weight in the problems that we've had so far, but it's super important. I know we had an exam problem on it, on this concept, and it's going to be reinforced in the next couple of weeks as well. So I'll explain apparent weight here in a sec, but someone said, is spring force will only be negative when it's pointing downwards? So, wait, what do you mean exactly? Because in this problem, for example, let's say the spring was like this, right? If I compressed it to where it's like this, right? This is delta y essentially. I'm pushing upwards, right? The spring force will be directed downwards, would be negative because it's trying to restore the original position. Yeah, so it's dependent on if it's compressed or expanded. Yeah, you're absolutely right. So if I, like I said in the example here, if I compress it to the right beyond its original position, the spring force is going to want to unwind it to the left. If I pull it to the left, the spring force is going to want to compress it again to the right. So it depends on delta x / delta y. Depends on if you're on like delta x or delta y is just dependent on like if you're in the x or y direction. But yeah, it's dependent on the value that you have, the sign that you have for delta x or delta y. So in that case, if like your delta y right here, you're pulling it downwards, so your delta y is negative, right? You're moving downwards, then the restoring force is going to be positive to oppose that. If it was positive, right, if I'm pushing inwards, my delta y is positive, then restoring force has to be negative to oppose that. Oh, that's not a negative sign there, negative. So it's just dependent on the value that you have, the sign for your delta x or delta y. But then apparent weight is the force that you feel, right? So you have a weight that's equal to mg, that's fine. Your apparent weight is equal to what you feel. And usually the best example that we give is with an elevator, right? So let's say, for example, this elevator is moving upwards, right? If it's moving upwards, what's the net force? Is it going to be positive or negative if it's moving upwards? Positive, right? And what does that mean for the, what's it called? What was I going to say? Oh, never mind. Yeah, for the acceleration, if we have So if it's F net y, for example, right, that's going to be equal to MAY, right? So it's not equal to 0 because it's moving upwards. So there's a net force upwards. And so that, let's say if we're looking at this person right here, this person has a normal force pointing upwards and a gravity force pointing downwards, right? So in terms of the person, just the person, their net force equation would be Fn minus Fg, right? But in terms of like what net force that they're feeling, well, they're moving in a net upwards direction, in the net y direction, right? Because that elevator is carrying them upwards. So in that case, if they're moving upwards with a net force upwards, right? We don't care about it. It's weird because you would assume, okay, well, Fg, well, why aren't we factoring in like the weight of the elevator or something? We're only like focusing on the person in this case. We're not interested in what the elevator's weight is. Because if we're looking at normal force, right? We want to figure out the normal force of the person. We want to look at the force of gravity of the person, their weight, and then relate it to what net force they're feeling. And so they're feeling an acceleration upwards, let's say of 3 meters per second squared or something like that, right? So the elevator is applying that net force, pulling them upwards, and then that person feels that net force. So if they feel that net force, we're going to want to relate what other forces they feel. And those forces are normal force and gravity. And so that being said, then if you want to look at adding Fg over, right, then you'd have MAY plus Fg is equal to Fn, right? So that would mean your normal force is actually smaller than your force of gravity, right? Or no, my bad, greater, sorry. It's greater than your force of gravity because it's equal to the force of gravity plus whatever net force you had, which is the MAY part. And that's why if you're going up an elevator, right, elevator's carrying you up second, third, fourth floor, right, you tend to feel heavier. And so that feeling, that apparent, right, so apparently I feel heavier. That's how I kind of think of it. Oh, I apparently feel heavier then. It's defined as a force that you feel. It's the magnitude of all supporting contact forces. What are contact forces? Really, it's just normal force. That's the contact force here because you're in contact with the floor of the elevator. So when I'm looking at apparent weight, I'm concerned with the normal force. So if I have a net force upwards, I have a positive net force, I can add over the Fg, and that shows me that if I'm traveling upwards, positive acceleration, net force upwards, I'm moving upwards, then based on my equation, then my normal force is actually greater than the force of gravity. Because if this was, well, I don't want to give values because then it would just make sense automatically. But let's say this was 300 newtons, right? This normal force, and this was 100 newtons, right? If I added over Fg, 100 plus Fg is equal to Fn, and I know this is 300, then Fg is 200 newtons, right? And so that's the idea here where my actual weight, I might actually weigh 200 newtons, but I feel like I weigh more, right? Because that elevator is carrying me up and applying some positive net force. So just think about the whole elevator idea when you're thinking about the apparent weight. So apparently I feel heavier when I go up an elevator, right? Because there's that net force that's positive, and if I add over the force of gravity, that force of gravity plus that net force is going to give me my normal force. So that indicates that my normal force is a lot greater than my force of gravity, or at least apparently it seems that way. That's why we call it apparent weight. So the man feels heavier than normal. How about if I'm going down with an elevator? What's my net force there? Positive or negative? So if I have a negative net force, what does that mean for my F net y? If I were to want to adjust this MAY, what would I have to do? Exactly. So it's a negative MAY, right? So I have a negative MAY here. So if I have a negative MAY, and this is still equal to Fn minus mg, right? Is my apparent weight greater than or less than my actual weight? Less than, right? Because then if I add over force of gravity, which is mg, then my force of gravity minus my net force should give me my normal force. So that means that if the force of gravity was 300 newtons and the net force was 100 newtons, for example, right? Or, well, I guess I want to say if this was negative 100 newtons, right? Because it's pointing downwards, obviously. And this was 300 right here. This was the minus 300. If I added the 300 over, 300 minus 100, that should give me 200, right? And so clearly you can see that the magnitude, normal force is 200 newtons versus gravity is 300. And so in that case, you can see that when you're going down an elevator, right, you feel lighter. You apparently feel lighter. Your apparent weight is lighter than your actual weight. You apparently feel that because there's this net force downwards with a negative acceleration causing a negative net force. And if I set up my equation the right way, if I add over that gravity, I can clearly see that my normal force is equal to my gravity minus my net force. Does that make sense? The whole light versus heavy, going up, going down. And honestly, you can just kind of relate it to real life because if you're going up an elevator, right, you feel a little bit heavier. If you're going down, you feel a little bit lighter. Do we have to worry about velocity? I don't think so. And well, maybe, I guess just for this example problem, it kind of depends. But let's see here. So as Marie has a mass of 50 kilograms, she gets into a 1,000 kilogram elevator at rest, steps on a scale. As the elevator begins to move, the scale reads 600 newtons for the first 3 seconds of the ride. Okay. Yeah, I mean, you might have to worry about velocity in some cases, but that would just be a matter of like they'll give you like some forces and stuff. You might have to figure out the acceleration of the elevator, for example, and they'll ask you maybe like, oh, well, the elevator started from rest. After 3 seconds, for example, what's its final velocity? And so you know if it starts from rest, it has an initial velocity of 0, and you know the acceleration after figuring out the forces. So this is kind of what is going on here, right? I know the scale, whatever the scale reads on an elevator, like this is the type of problem. Since you have this scale, a scale will represent or show your apparent weight. It won't show your actual weight on an elevator if there's a net force upwards or downwards or whatever. Otherwise, that's why like if you step on a scale and there's no net force, like if you're just at home and you measure your weight with a scale, you're going to get an accurate measurement. But if you have a net force upwards or downwards, the scale is going to show you that apparent weight. So in this case, the apparent weight is 600 newtons, for example, right? And so I have to set up that similar equation where I did earlier and then figure out my acceleration. I know that I started from rest, for example, 0 meters per second. I use my acceleration to use the amount of time, for example, to figure out a final velocity, or I could figure out some distance traveled using the other kinematic equations. Yeah, the scale is just showing the normal force the person has on the scale, the normal force. And in this case, when we're talking about normal force, especially in an elevator context, right, and there's a net force upwards or downwards, then we're talking about apparent weight, because apparent weight is the magnitude of all supporting contact forces, and normal force is a contact force. Yeah. Yeah, eventually you're just looking for displacement. How far is the elevator moved? And so in order to get that, we have to find out what the acceleration is. From the acceleration, you can kind of use your kinematic equations to figure out some velocity values and some displacement values based on what information is kind of given to you. So that's how you'll relate like the Newton's laws problems to some older stuff that we did in the first couple of weeks with kinematics. Yep. But that's kind of it for the apparent weight stuff. Friction, kinetic, static, rolling. Kinetic is sliding friction. Static is going to keep you from slipping, like I said earlier. And the idea of the static friction force here, force that exerts on an object to keep it from slipping. And so you only witness that maximum static friction force, like we had that problem, right, where there's like a minimum pushing force, for example, right? Or if that box is just about to slip. And this is what I was talking about earlier, where it says friction adjusts to be as big as it needs in order to keep the object from slipping over the surface. So that's why it was a little kind of confusing, because like when I was saying about the object pushing up against the wall, right? If I push really hard, the static friction force doesn't need to put a lot of work in. It doesn't need to kick in, basically, to prevent the object from slipping as much. But as soon as I start to relieve that pressure, the static friction force is like, okay, oh shoot, we're slipping. I need to rev things up a bit, right, to prevent the slippage. And so there's a maximum possible magnitude to that static friction, and that's equal to mu times the normal force. And that makes sense because the push force that I applied, let's say that was 300 newtons, there's a normal force that is applied back to me, opposite and equal, from the wall, right? And so if I decrease that normal force, right, to a certain point, or if I decrease the pushing force, I decrease the normal force, and that normal force decreases to a certain point, right? That's where the static friction force will have to increase to kick in and prevent the object from slipping. But yeah. Yeah, I guess. Let's see here. Objects on slopes, tilted coordinates. Same idea here with tilted coordinate stuff. We did a bunch of those now. This is a really good example. Yeah, this one should be marked for sure, because this integrates the static friction stuff, the tilted axis stuff, and it even gets you the maximum static friction force. So it'll say like icy conditions can cause mu to decrease even further. How small can mu get before the car begins to slip? So kind of an integration of all that stuff together. And so that's a really good problem, and I'll for sure upload this so you guys have access to that one. Yeah, go ahead. This one? This one? I haven't, no. Would you like me to? Okay, yeah, I can go over it. So it says a car with a mass of 1,200 kilograms is parked on a slope which makes an angle of 10 degrees to the ground. It's been raining, so the coefficient of friction is mu equals 0.4. It's asking for what is the force of friction on the car, right? So in this case, in order to figure out the force of friction, we can't necessarily, like I said, just immediately jump to, okay, force of friction, the static friction at least, is mu times Fn, and just do that and be done with it, right? We can't necessarily say that, because the static friction force that's being applied currently is dependent on the other forces acting against it, basically. So if you have this tilted axis, right, we have normal force pointing upwards, FGY pointing downwards, FGX like this, and FS like that. So there's the static friction force, right? And so F net X equals 0 because the object is, or the car is not in motion, right? It's parked. And so we have this FGX minus the static friction force. And so static friction force is equal to FGX, right? So in that case, your static friction force would be equal to the FGX to keep it still parked and not in motion. That's how you'd figure out force of friction, right? That's the 2.1 kilonewtons. Now, when they ask you, is there any... Yeah, go ahead. Kn is just kilonewton, so that'll, like, once you calculate it out, you'll get 2,100 newtons. And so if you just divide by 1,000, that's 2.1 kilonewtons. But, I mean, yeah. No, absolutely not. Unless they require it for it to be in kilonewtons, which is really rare. No, you won't get points off. Mm-hmm. Yeah, because, so in this case, right, we're concerned with what's actually going on, because we just know that the car is parked. There's no indication yet, based on what's given to us so far, that the car is about to slip. The only time we use that equation, like I said, the Fs max, is if the car is indicated that it's about to slip, or if that box is indicated that it's about to slip, right? So that's the idea there, right? Because in part B, for example, that's where we start using the FS max, because, or at least the concept of FS max for B and C, because we're wondering now if the car is about to slip, right? So you only use FS max if there's an indication that the car or the object is about to slip. Otherwise, your FS will just be calculated based on the other forces acting in its direction. So if FGX is acting in the X direction, FS is acting in the X direction, I would calculate FS based on the relation of the other forces acting in the X direction. Yep. So the only time you ever use FS max is if it's about to slip. If something's about, like, literally they will almost always say slip or about to slide or something like that. So for part B now, they're saying, is there any danger of the car slipping down the slope? Justify your answer with a calculation. So if we were to calculate the FS max, right, this is the maximum static friction force, right? We take the mu, which is 0.4, times the normal force, and we can get that via trig. I won't go into detail with that, but you have the mass, you can figure out the gravity, you can figure out the FGY and get the FN, because they'll cancel out there. And so if you multiply mu times Fn, you should get your maximum static friction force. And so your maximum static friction force is 4.7 kilonewtons. So that's the friction force that's going to be applied just right before the car is about to slip. So that's where I was saying, like, this whole force is variable, because look, the car here is parked, right? So when it's parked, there's a static friction force of 2.1 kilonewtons, or 2,100 newtons, right? If that car was about to slip, then it's kind of like that problem with the box, right? If I relieve some of that pressure, right? Maybe let's say if I wasn't parked, if I had the brakes on for something, or for example, right, if I have the brakes on, then, and I start to relieve a little bit of that pressure from the brakes, then maybe my FGX, I don't want to say increases, because it's a little weird. I don't want to say that, but basically the car is about to slip. Let's just say the car is about to slip in that case, and if it's about to slip, right, or if I'm relieving some of that pressure, then the static friction force is like, oh shoot, I'm about to slip. I have to ramp things up, and so that's why you have this maximum static friction force of 4.7 kilonewtons. And so, since there's a maximum of 4.7, if the static friction force here, when it's parked, is 2.1, then it's not at its maximum yet, and so it's not in danger of slipping. It's in danger of slipping when the static friction force is at its maximum, because that point it's like static friction force is like, guys, I can't hold on to this any longer. I'm about to slip. I'm at my maximum. That's the idea. Does that make sense? Yep. And so that brings us to C, where they're saying icy conditions can cause mu to decrease even further. How small can mu get before the car begins to slip? So then we look at our, what's that called? For some reason, I just totally blanked out. Static friction force, yeah. So, hold up. Did I calculate this wrong? Icy condition could cause u to decrease even further. How small can mu get before the car starts to slip? Oh, no. I see now. So I think you would still use the force of friction from A. I think. You wouldn't use the maximum static friction force yet, because they're just asking about like the original condition, and they're asking you how small can the coefficient of friction get before it starts to slip. But hold up, I want to check this real quick, because maybe I messed something up. Yeah. So I was saying right. So we've seen static friction force is 2 kilonewtons. As mu decreases, so does the maximum static friction force. So once this maximum static friction force decreases below 2 kilonewtons, the car will slip. So the smallest mu, which will keep the car stationary, is one where mu times Fn is equal to 2 kilonewtons. So yeah, so it's just saying, like, C is basically telling you to imagine that the answer from part A was the maximum, and then, like, let's say, okay, that makes sense. So if, for example, we have the pavement on the road, right? If you have this thing parked on the road, right? Or if you're moving on the road, for example, and then it starts to snow, layer of snow comes between the tires and the road, right? Well, that like will start to um, like decrease the coefficient of friction, for example, right? So in that case, let's say you're originally like you have that 2.1 kilonewtons, right? That's your maximum static friction force. That's what was calculated. But now the condition of the road itself, which is a property of the road, it's not a property necessarily, or like it's not a value that we can calculate necessarily in terms of like being at a maximum or a minimum. It's just the mu is a property of the road itself. So let's say like it's a chemical property or something like that. It's unique to their style or unique to the condition of the road. So if that mu decreases and we know that this maximum, let's say the maximum was 2 kilonewtons based on part A, then how low can mu get before we start to slip? And so the normal force that you would put down is the normal force that we calculated with the FGY part. So yeah, they're just asking you like to use part A basically to figure out what the minimum mu value would be, assuming everything else stays the same. But yeah, that's the friction stuff. Yeah, go ahead. Yeah, because then icy conditions, you're decreasing friction, right? Because things will just start to slip and slide. It's kind of like the stiffness for the spring stuff. But yeah, that's more of the slope problems. Newton's third law. Highly recommend doing this box stuff and watching my review for the written homework, I think it was. Yeah, because I go over the action-reaction pair stuff. When you have like a force pushing on one box and the other force feels the other force and stuff like that. Yeah, larger the K, the more stiffer the spring. So I don't know. For this action reaction pair stuff, it's like really long-winded, and I explained it like really thoroughly in the last written homework review. But just as a summary, I guess, if I were to push on this box with, you guys remember that 250 Newton problem with the two boxes? You guys remember that, right? Okay, yeah. So if we were pushing with 250 newtons, right, on that box, A feels that 250 newtons. B will still get that 250 newtons applied to it because the two box system, they move with that net force of 250 newtons. It'll have the same acceleration. But B doesn't feel those 250 newtons, right? Because we're only interested, like if we're looking at what B feels, we're only interested on what B feels necessarily relative to what it comes in contact with. So the hand in that problem came in contact with A. A feels that 250 newtons. B doesn't feel that hand. That hand doesn't touching B. What is touching B is box A. And so it's kind of like the idea of just looking at specific perspectives. So from the perspective of A, it feels the force of that hand pushing on it, and it feels kind of this normal force of B on A pushing back onto it. So if you have like people standing on a line, you have this first person, second person, third person. Let's say the first person is like your hand. This is like box A, box B. So the first person bumps into or pushes the second person here, right? They're going to feel that 250 newtons. They're going to be aware of that. And if person A bumps into person B looks back, they're not going to look at person 1. They're going to be like, "Hey, what the heck, man? Person 2 bumped into me," right? They're not aware of person 1 instigating the action. So from the perspective of person 3, or box B essentially, right? They're going to be concerned with what they came into contact with, which is box A, or that second person. And so the reason why in that problem we were like looking at the idea that the force that B felt wasn't the actual full 250 newtons. The reason why is that if you were to kind of think about this as if that hand pushing on, let's say you had like a really heavy couch or something, or a really heavy object, right? If I pushed on that heavy object with 250 newtons, sure, it's going to feel 250 newtons, right? Now, let's say maybe I pushed it with 250 newtons, and I was, I guess someone was in front of that couch or something, or that object, right? And I was just barely able to move that box with 250 newtons, and then that person got hit by the box, for example, right? Well, that person isn't going to feel that 250 newtons necessarily, right? The couch felt the 250 newtons from its perspective. The person, right, didn't feel the full brunt of that 250 newtons. They just felt what the couch basically like bumped into it with, or bumped into them with, right? So it's the whole idea of perspectives, like, right? Think about what each box is feeling. The box A is feeling the pressure of the hand, and it's feeling itself bump into B. Box B is only feeling box A bumping into it, right? And it feels based on its mass. So box B feels the force of A based on its mass. So if I'm calculating like force of A on B, right, I can't say that's 250 newtons, which was the hand. I'd have to calculate, okay, what's mass B? That's my perspective. I'm looking from what I measure on for my mass, right? And then multiply that by the acceleration that I'm feeling due to that overall motion, right? Because the boxes are moving as one system. So let's say if the acceleration was 2 meters per second squared, we're both moving at that 2 meters per second squared. We have that like that momentum, right? Because if that person, if we were going back to the idea of people in a line, if the first person pushed me, box A, box B, they're going to bump into B with kind of like that momentum with that 2 meters per second squared, right? But box B is going to feel a little bit different because, say, for example, I thought of another good example on the spot. Because if person one was just a decently sized person, right? Person two was like, I don't know, let's say a very scrawny person. And then person three is The Rock, right? If they're Dwayne Johnson, that person one is going to push person two. That person two is going to go flying. That's still 250 newtons, right? But then person three, The Rock, I don't think The Rock is going to feel that 250 newtons. That man will not budge, right? We're still kind of moving together with that 1 meter, 2 meter per second squared, but from the perspective of The Rock, from that perspective of that box, right? Maybe The Rock weighs, I don't know, let's say 80 kilograms or something, right? Well, he's going to, from his perspective, right, the mass of The Rock times that acceleration, he might feel a different force than that person who got pushed initially felt. So it's a matter of perspectives, looking at what each person feels, kind of like from a selfish perspective. So that first person, that box A, feels the hand. It feels the full brunt of that force. Box B will only feel what it feels from box A based on its mass, based on its own characteristics, based on its own perspective, basically. But yeah, that's kind of the idea with the action-reaction pair stuff, especially with the boxes. Highly, highly recommend going over that written homework problem with the boxes. And then there's an example of it in your group practice problems from discussion as well. I would go over that too. And there's another problem that's like that in the practice exam that I'll be sharing as well. But yeah, this is more static friction stuff. This is more of the objects moving with each other. But that's it for what to review on the slides. For the written homework problems, like I said, I would make sure to really review problem 3 again, because it's those two boxes. This is like the hippo problem again. I'd review this one. Honestly, I mean, I really don't have to pick out problems from the written homework. I would just strongly recommend always reviewing all the problems from the written homework, because they're very reminiscent from the quiz. But if I had to pick out two that seem really important, and are just a little bit more challenging to think about, problem 3 and problem 1, and then maybe like part B of problem 2. The idea of finding the maximum mass and stuff, because there's different components that go into that. For the online homework, I would take anything that talks about springs just to review. Problem 4 is multi-step. I got a lot of questions about problem 4, and so I'd recommend going over that as well. Let's see here. This problem 1 is good because has a lot of the forces kind of interacting with each other, and it's a little bit long-winded, so it's good practice mathematically for Newton's laws again. Yeah, this is spring force, so anything with spring force, still review it for sure. More spring force there. This is more conceptual for spring force. The apparent weight stuff, this is conceptual for the apparent weight, but it is very, very helpful in understanding the apparent weight again. And this problem is just weird. I guess you might want to go over it, but it's more, once again, of just combination of the Newton's second law stuff again, and yeah. But I think that's it for what to review, what's important and stuff. Okay, I am so beyond thirsty, so I will probably stop the recording now, go get a drink of water, and then I guess if no one has any other questions, you guys are free to leave. And then if someone has a question, or if you guys have any questions, just feel free to stop by. We have 3 minutes left, so I might not be able to stay for too long, but yeah, hopefully that was helpful. Okay, let me stop the recording now.